Welcome back to ISY 6382. In the previous lesson, we learned what DOE is and how we can use it for process improvement. Today, we would like to talk about several designs that we used in design of experiment. Specifically, we talk about one factor and a two-level factorial design experiment. So if you have only one factor, we reviewed the technique that we can use for analyzing one factor experimental design, and that technique is ANOVA. And we reviewed the ANOVA in analyze phase. And if you remember, we had one hypothesis testing saying that if we have, let's say, one factor, factor A, and it has A different levels, 1 to A, if the mean of response for all these levels are the same, it means that factor A is not affecting response. So if H null is not rejected, the factor is not significant. And we had an ANOVA table, and based on this ANOVA table, we could calculate the components of variation, and based on that, we could compute F naught, and F naught is if F naught is greater than some threshold, which follows an F distribution, then we reject H naught. Otherwise, we cannot reject H naught, and factor is not important. If we do reject H naught, then factor A is significant, and we need to find a setting which maximizes or minimizes the response. So what happens if we have more than one factor? For example, let's say factor A at A level, as you can see, 1 to A, and factor B at B levels, 1 to B here. And what we do, we try to run some experiments randomly for each cell, with some replication. As you can see, this N is the replication, and we can have a two-way ANOVA with interaction to see if this factor A, factor B are significant or not. And as you can see, we can calculate 3F ratio or F naught. The first one is basically mean square of A, which is related to factor A. If this is greater than some F alpha with A minus 1 and AB n minus 1 degrees of freedom, then factor A is significant. We compare the second one with B minus 1 and AB n minus 1. F naught, the second F naught, which is related to factor B, is greater than this threshold. We reject H naught, meaning that factor B is significant. And finally, we do another hypothesis testing for interactions. And if F naught, which is MSAB divided by MSE, is greater than F of alpha, A minus 1, B minus 1, and AB n minus 1 degrees of freedom, if it's greater than that, then they have also an interaction effect. But multiple level designs are not always the best case for conducting design of experiments. The reason is as follows. Sometimes we have more than two factors. In reality, we have 5, 6, or up to 10 factors. So let's say we have 5 factors, and each factor has 3 or 4 levels. Let's say 4 levels, so we have 5 factors and 4 levels. Then the total number of treatment combinations that we have is 4 to the power of 5. And if the number of replicates is, let's say, 3, then the total number of experiments we should conduct is 4 to the power of 5 times 3, which you can see it's a considerable number of experiments. And it requires basically money and resources for conducting this experiment. However, we may end up seeing that only 2 of these factors are significant. So instead of starting with multiple levels, we can start with 2 levels and do some screening. So we may start with 10 factors, which we think they are significant. But instead of going multiple levels, we can just start with 2 levels. So number of levels would be 2. And then we can start with some replications, 2 or 3 replications. Then it can give us a smaller number of experiment necessary compared to multiple level factors or designs. As you can see, we have 2-level factorial designs or 2 to the power of k designs. These are also known as a screening design because we can screen the high number of factors and make the number of experiments and number of actual influential factors smaller by doing a relatively a smaller number of experiments. 2 to the power of k, 2 is the number of levels and k is the number of factors. So we have k factors and we have 2 levels. Here is one example. Let's say we have 2 factors and it's a router experiment, and we want the response variable is vibration. We want to measure the amount of vibration, and we want to see whether these 2 factors are significant or not. So in this experiment, k, which is the number of factors, is 2. Level is also 2. So we have a 2 to the power of 2 design, which is 4 treatment combinations. And as you can see, there are 4 combinations. In this example, n, which is the replication, is 4, and in total we need to perform 16 experiments. As you can see, there are 16 numbers here in this table. We have 2 factors, factors A, and usually in 2 to the power of k designs, we denote the factors by level of factors by negative and positive. So A has 2 levels, low level is negative, high level is positive. B is another factor, low level is negative, and high level is positive. So it's low, high, low, high. Then different combinations, you can see both of them at low level, A at low, A at high, B at low, A at low, B at high, and both of them are high. So if we want, we can show this design on a square. So we can say this is A and this is B. This is low level of B, this is high level of B. This is low level of A, this is high level of A. So the 4 corners, each corner corresponds to one basically treatment combination. A little bit of notation. Whenever B is at high level, we use little b to denote that, and whenever A is at high level, we use little a to denote that. So for example, and if they are at low level, we use 1. So if A at 1 is at low level, B is also at low level, we have 1, because both of them are 1. When B is high, A is low, so it's going to be B times 1, which is B. If A is low, if A is high, B is low, which is this corner, it's going to be A times 1. And if both of them are high, it's going to be A times B. So as you can see, each treatment combination can be denoted by a letter or a number. So both of them high, AB, B only high, B, A only high, A, and both of them low is 1. Now here we also have total, so it's row-wise summation, as you can see, which is total of this number. We can also calculate the average for each treatment combination. That's the setting that we use for 2 to the power of 2 design, or in general 2 to the power of k design. Let me introduce you some terms. The first one is main effect of each factor. So basically what it means, it would be the when we change the level of a factor, what would be the effect on the response variable? That's called main effect. And how we calculate the main effect for each factor? So the average value when one factor is at a high level minus the average value when that factor is at low level. Okay, if we have, let's say we have this design, this is 30, 40, 20, and 10. If I want to calculate the main effect of A, what should I do? I take the average when A is at high level, because you know that this side, A is at high level. This is 35. Take the average when A is at low level, which is 15. Then if I subtract them, 35 minus 15 would be 20. And this is the main effect of factor A. I can show this on a plot where x-axis is the factor. I have 2 levels, negative and positive, and y-axis is the average response. And as you can see, the average response when A is at low level is around 15, and this guy is 35. So the slope of this line, or basically this here, is the main effect of A. We can do the same thing for B. As I said, the average at high level, this is AB, this is A, this is 1, and this is B. So the average would be A plus AB divided by 2n, and n is the replicate, B plus n divided by 2n. So I can write down the main effect by using this term, and as you can see, this term, this is a kind of a constant. We call this term in the parentheses, we call it contrast. So it's contrast of A. So whenever we say contrast, it means summation of high level minus summation of low level. We can have a similar formula for calculating effect of B. As you can see, this is the contrast of B. Another term which is useful and you've seen before is interaction effect. So what is the interaction effect? As we discussed before, if the effect of one factor is constant at the level of other factors, then there is no interaction effect. If the effect of one factor is varying by changing the level of other factors, then there is a significant interaction effect. Here is two examples that we have. So let's say in one design we have 10, 30, 40, and 20. And what I'm going to do, I'm going to plot something called interaction plot. And this 30 is the average of all the experiment when A is at positive and B at negative, and so on and so forth for other corners. So as you can see, this is the interaction plot. We have factor A. So this side is factor A negative, this side is factor A positive, and I plot two different curves. One is for B at negative level, one is B at positive level. So let's say B at negative level, which is these two numbers. When B is at negative level, when we change factor A from negative to positive, so negative is 10, as you can see, positive is 30. So what would be the effect in that case? Is around 20. So that's the effect of, I can say this plot shows the effect of A at the low level of B. Now let's focus on high level of B. When B is high level, A is low, then this value is 20. If both of them are high, this value is 40. So this curve shows the effect of factor A when B is high. And as you can see, these two effects are the same. So the effect of factor A does not depend on the level of factor B. So the interaction here in this case is not significant. Another example here, you can see when B is at low level and we change factor A from negative to positive, so that's the effect. And when B is at positive level or high level and we change factor A from negative to positive, then this is the effect of factor B. And as you can see, the effect of factor A when B is at low level is the positive effect because it increases the response. However, the effect of factor A when B is at high level is negative because it decreases the response. So in this case, we said interaction, there is a significant interaction between A and B on response. So how can we calculate the interaction effect? Again, it's going to be the average when AB is positive minus the average when AB is negative. So what do I mean by that? Let's say I had this A and B, you remember this, A negative, B negative, A positive, B negative, and both positive. So we can define a column, which is AB, and we multiply those signs. Negative multiplied by negative is positive, positive multiplied by negative is negative, negative, and positive. So what is this guy? This guy is 1, this guy is A, this guy is B, and this guy is AB. So the average at the positive level means the average of these two guys, which is AB and 1, and that's what you see here. And the average at the negative level are these two, which is A and B, and what you see here. So that's the equation for calculating the effect of AB or interaction effect, and this is again is called contrast of AB. So we have contrast for main effects and we have contrast for interaction effects. Now let's see one example and see how we can analyze it. So we can calculate the effects easily for this example. The effect of A is calculated by this equation. So A, in this example, A would be the summation or total number here, which is 96.1. Then B, AB, which is this number with positive sign, and B and 1 with negative sign. So we can use this equation. 2 is here and n is the replicate. We have 4 replications, so we can easily calculate the effect of A, which is 16 in this example. We can similarly calculate the effect of B, which is 7.54, and AB, which is 8.71. So as you can see, if I want to sort them, I would say A is the most influential factor, and then after that, interaction effect is more important than effect of B. However, the question is whether those numbers are significant or statistically significant. We know that the effect of A is greater than B, but we are not sure if it's statistically significant or not. For that, what we need to do is to perform some hypothesis testings. And here, the figure that you see is the effect of interaction plot. That's just one example. How we can do hypothesis testing? The hypothesis testing is being done by, again, ANOVA. And you know, for constructing the ANOVA table, we need to know sum of a square of each component. Using the notation that we had before, and based on defining the contrast, we can easily find those sum of squares. Here is the general equation for sum of squares. Basically, it's a contrast squared divided by n times summation of contrast coefficients squared. So if I want to calculate SS of A based on this equation, SS of A would be contrast of A, as you can see, A plus AB minus B minus 1. That's the contrast of A that we had before. And N summation of contrast coefficients squared. So the coefficient here is positive, here is positive, here is negative, but a square of negative would be positive, and here the coefficient is negative. Again, it's going to be a square. So if we add them up, it's going to be 4, and that's why we have this equation for sum of a square of A, for sum of a square of B, and sum of a square of AB. We can easily calculate each component, and then we can finally construct an ANOVA table, because we know that in an ANOVA table we need to have SS of A, SS of B, which is the speed of router machine, and SS of AB, which is for the interaction, and we have sum of a square error, and we have sum of a square total. So now the question is how we can calculate sum of a square error and sum of a square total. For sum of a square total, we can easily find the sum of a square total by this equation. So you pull all data together, everything, and you calculate 1 to capital N. So you pull all data together, you combine them, then you take the average, that's going to be y bar, and each component minus average squared, and you add them up, then you get sum of a square total, and sum of a square error would be sum of a square total minus SS of A minus SS of B minus SS of AB. Then you have the degrees of freedom. This is very similar to what we had in ANOVA. That's the same thing, because we have, it's a special case of ANOVA. We have 2 factors at 2 levels. We can calculate the degrees of freedom exactly as what we did in ANOVA table. We can find the mean square, we can find F and the corresponding p-values. And in this example, since p-values are less than 0.05, then all of them are significant, and all of them are statistically important factors affecting vibration. Now let's see how we can use Minitab to do 2 to the power of 2 experimental design. Now first of all, let's see how we can design an experiment, and then the second step would be how to analyze it. So we go to a stat menu, DOE. We are talking about factorial designs, and here we want to create a new factorial design with 2 factors at 2 levels. So we have different options here. What we are trying to do is a two-level factorial design with default generators, and number of factors is again 2. So we go to designs option, and here we can basically tell Minitab what is the number of replications. We select 4. If we want, we can have blocks, but here we don't have any blocks, so we use this one, and we are using full factorial design. Push OK. So here in options, if randomized runs is basically on, what would happen, and I'm kind of like checking this option, what would happen, it gives you a random order of experiment. So this is really good. If you want to do randomized order, you can start with this one. It gives you a randomized order, you conduct the experiment, and then come back analyze it here again. So let me push OK and OK here. If I go back to the worksheet, here as you can see, we have factor A, factor B, and at different levels. And as you can see, it's random because positive, positive is the first level, then second level is negative, positive, and then negative, positive again. So it's not order, it's kind of like a randomized order we have. This is the run order, so we should use this order for, it's the order of conducting the experiment. And if we didn't have a randomized order, that would be the actual order of this row. And we don't have any center points, and the blocks are always 1. So we can just get rid of these 2. Now, one thing else is if you want to define the name of factors and the type of factors, you can do it here. So if I want to, I can change factor A, for example, to time, factor B to, let's say, type of material, and I can say whether it's a numeric factor or it's a text factor. And I can define level low and high. Default is -1 and +1, and we prefer to use this default. Now, let's say we already conducted the experiment and we entered the data here, and we want to analyze data. So we go to a stat, DOE, factorial. Now we want to analyze factorial design here. We select the response. So in terms options, you can see we have 2 factors, and we want to analyze main effect of A, main effect of B, and the interaction effect. And in the graphs menu, you can do residual analysis to see the assumptions that we have for ANOVA is valid here or not. That's very similar to ANOVA analysis. Otherwise, you can just push OK, and here is what you get. So first of all, we have a Pareto chart showing the effect of each factor. A is the most important factor, and it's around 13. Then it's AB, and so A is 13.6, AB is around 8 or 7.1, and B is around 6.16. And here is the threshold. So if this passes this threshold, the effect is significant. Now we have some ANOVA analysis again here, effect of A, effect of B, effect of AB, and the p-values corresponding to that shows whether this is significant or not. Actually, as a matter of fact, the ANOVA is here. So this is linear effect, which is effect of A, effect of B, the p-value is 0, the p-value is 0, and this is for AB, again the p-value is 0. Here linear means whether the linear or main effects, any of main effects are significant or not. So if the p-value of linear is greater than 0.05, means none of the main effects are significant. Here also we have we can have the same conclusion or same analysis for interaction effects, two-way interaction effects. With that, we finish this lesson. In the next lesson, we learn how to extend this factorial design, two-level factorial design, to higher number of factors.